I'm going to let Leo introduce himself, but I just wanted to make sure that that you know how much Soap Lake Conservancy appreciates you coming today, and also to do a plug. Some of you are not from the area, some of you are from further away. I want to encourage you, since you're here today, that means to me you have an interest in the lake and that you have an interest in its health. And so I want to encourage you to seriously consider becoming a member of Soap Lake Conservancy. Soap Lake Conservancy is the only, and it's a 501c3, it's a nonprofit, tax-exempt organization. You don't have to be a member, you can just donate your money. You don't have to donate your time. Sometimes time is more precious, I understand that. But it is the only organization that really is ready to fight to save the lake. And we are. So if you have that interest, it's not fight in the sense of something else has to be diminished. It's fight in the sense of advocacy, of educating and publicizing and building coalitions for the diversity that's absolutely essential moving forward in time. And so please consider supporting this effort with more than just your presence today, although I do appreciate your presence today. My name's all over, my phone number's all over. You can talk to the president of the board here. You can get a hold of people you know that have been in the Conservancy. It's time. This is the time, and you're here. So thank you. Leo Bodensteiner.
Thank you. My name is Leo Bodensteiner. I'm a professor at Western Washington University. And I was one of the participants in the study of Soap Lake back in the early 2000s. Another one was Dr. Anthony Gabriel, who's a professor at Central Washington University in geography. And he and I do lake work together. And we were out in Wisconsin at the time that Dr. Holly Pinker she's a biology professor at Central. And she got a National Science Foundation grant to look at the life in Soap Lake. And she gave us the opportunity to look at the lake physics and chemistry. And so Tony and I took that on, and we did just about 3 years of work on the lake. We came over once a month and did our measurements. And I'm going to talk a little bit about Soap Lake. I have a limnological gem on here. I didn't know anything about Soap Lake when Tony asked me, hey, you want to study Soap Lake? And I said, sure. And I had a grad student at the time, and his wife was trained in limnology at our University of Idaho. And she says, Soap Lake, it's a limnological gem. Hey. So I've learned a lot about it since then. Anyway, I wasn't clear on exactly audience, and so I may have way more slides than I need, but I have a little background on Soap Lake, so I'll start with that. I should start with limnology is the study of fresh water. Includes lakes and streams, physics, chemistry, biology, so that's what limnology is. And I teach limnology at Western. It's my fall quarter course, so I've been doing that for 20-some years. So, am I going to advance the slides? I will advance the slides. You know where you are. Probably don't need this slide. There's going to be a quick one. We're at Soap Lake, Central Washington, so next one, please. So, down the road. Why is Soap Lake a gem? So, next. Is it the diversity of fish, wildlife, and wetland plants being extraordinary? This could be multiple choice. Next. The world's largest lava lamp will be found in the city of Soap Lake, Washington. A future spaceport will be built nearby, and returning shuttle passengers will be welcomed by a view of the lake. Or Soap Lake water has magical healing properties. So, to review, D, maybe. Let's see what A says. A. There are no fish. There are no fish in Soap Lake, and there are no plants either. There are a few organisms that are able to live in the waters. None of these. So no. B. Space shuttles. We retired that fleet a while ago. So maybe next round, maybe for the Mars exploration, they'll land out here at the Lewis County Airport. It's the water, and people have been coming over to Soap Lake, I think, since way early last century, even taking the trains here to take the muds and soak in the water. And I understand people used to run their cattle into the water to remove the flicks, fleas, and ticks. Just a brief yes.
Can you speak up just a little bit for us back here?
Thank you.
I guess I can.
We need to make it a little taller though. There we go. I got it.
Hello. Okay. All right. Just a little bit of background on Soap Lake because it does have some unusual properties among freshwater lakes, or sort of freshwater lakes. The ice sheet, Cordilleran ice sheet, 13,000, 15,000 years ago, diverted the Columbia south down through the Coulee, down through the Grand Coulee. And glacial Lake Missoula, which is the giant lake that covered part of western Montana, had ice dams, and occasionally the water would rise high enough that ice dams would lift up and giant floods would come across to the west, flooding across eastern and central Washington. I think, I'm not a geologist. I understand there's something like 40 of these floods. It wasn't just one flood, but many floods. And when they did flood, they came down through Dry Falls area. And what I've read is that the amount of water that came over Dry Falls at any given time during one of these floods exceeded the flow of all the rivers of the world at that point. So big floods, moving lots of things. The substrate out here is all basalt laid down in the Miocene era. And you go back one. Thank you. And so with the basalt and with the rushing water, it forms in limnology. There's lots of different ways. We talk about lots of different ways to form lakes, and these are called erosion potholes. Essentially, usually not on the scale that you have here in the Grand Coulee, but the water dips and it scours out the bottom and it rises up and has rapids, and so the erosion potholes are what's left. And Soap Lake is the last, the southernmost of the erosion potholes that were formed below Dry Falls during these floods. And post-glacier, of course, post-glaciers, the Columbia River went back north to its former channel, and it left this dry valley dotted by these erosion potholes with some water in them. There's Falls Lake. I thought that was just a beautiful picture, so there you go. Falls Lake at the upper end of the coulee. And there's the lower Grand Coulee, and the series of these lakes, Soap Lake being the southernmost and the last on the list there. But you can see how the erosion potholes formed all the way down. Soap Lake is the deepest of these. So during the 9,000 to 5,000 years ago, there was a period of warmer, dry temperatures called the Holocene climate optimum. And they now refer to these as mega droughts. And there's a couple different theories about how Soap Lake formed and how it exists today. But one of those is that there was an existing body of water during these mega droughts. The outflow from the lake ceased and the water evaporated, concentrating the salts in the lake down to a much smaller lake. And then after 5,000 years ago, we entered a cooler, wetter period, and so inflow to the lake began again, precipitation returned, and freshwater, being less dense than salt water, overlaid that original lake. The original lake being the salty, dense, salty layer, and then the freshwater over the top of it. There's other ways for these kinds of lakes to form. That's just one likely one. I know there's a paper published back in 1955 where they speculated it had to do with freezing, perhaps, freezing causing the salts to be excluded to precipitate and settle. That's another possibility. But there was this is also the way that many of these types of lakes formed, is during this dry period, warm dry period, evaporating and then having fresh water on top of that. So the lake became chemically stratified. You have the really salty old lake on the bottom, and you have a fresher lake on top, fresher water on top. And that condition is called meromixis, or meromictic lake. So it refers to the stratification where you have two of these. You have the bottom lake and the top lake. And if you look at U.S. Forest Service documents, there's maybe a couple hundred of these. There's probably a lot more than we realize because it's not that easy to find them. But there's at least a couple hundred across North America that have been identified, and some of them have been studied pretty intensively. So you have a meromictic lake. The original lake is now isolated on the bottom, and in limnological terms that's referred to as the monomolimnion. And it has a boundary layer, and essentially it remains intact. It's very difficult once you get the boundary layer there and you have this chemical soup at the bottom. It does not mix. And then you have a layer above that that does mix, and that's called the mixolimnion. So you have the circulating fresher layer above it, and you have the dense salty layer below it. And some people are under the perception, oh, it's a salty layer like seawater, and every one of the meromictic lakes has a chemically unique signature because of the geology that they formed in. And so I just put this up here. This is, it's on the, I have a list of some of the chemical constituents: sodium and magnesium, calcium, potassium, strontium. Those are common things you find in seawater. And it is not seawater. As you can see, if you look at seawater on the left there and you look at the numbers on the right, seawater has something on the order of 10 grams, 11 grams per liter of sodium, where Soap Lake has on the order of 62 grams per liter. So it's not just concentrated seawater, it's some unique combination of minerals that come from the landscape around here. That's just a handful of them. This is just a diagram that shows, this diagram shows what a meromictic lake would look like. And this would be during the summertime, and this is not unusual for Soap Lake to exhibit these characteristics. It doesn't every summer, but some summers it does. You have thermal stratification that occurs where you have warm layer on top and you have cooler water below that. And in Soap Lake, below that even, you have this dense monomolybdenum, the chemical layer. So I'm going to walk over here. I'll just have to talk more loudly. So here's the thermal layers, and red is warm and blue is cold. And so during the summertime, you have a warm layer on top, then you have a boundary layer, then you have cool water, and below that cool water, you have the chemically dense layer down here, the monomolybdenum. So many lakes, any lake, you know, on the order of deeper than 60 feet, depending on the size of it, will show this during the summertime around here in the temperate latitudes. The unusual thing about Soap Lake is it has this layer below this. So this breaks down in the fall. The temperatures in the fall, the top layer cools off, the wind blows, and the lake circulates. But it only circulates down to this layer right here, that's labeled the chemocline. So that's the boundary layer that doesn't, below that it doesn't circulate. Okay?
You can remove the mic if you want to
Oh.
hold it.
And then at the end I'll drop them, right?
There you go.
Okay. All right, so this is just to show the point. This is some of the work that Tony and I did, and so we have a typical limnology graph here. In a limnology graph, you put depth on this axis, and you always put 0 at the top. That way, it's sort of like visually similar to what you see in the lake. So here's the surface of the lake. Here's the bottom of the lake. And this is temperature across here, and I've also labeled dissolved oxygen. I'm just going to look at temperature right now. And temperature are in the circles, and so this is the temperature. Here's 25 degrees Celsius, which, what would that be? Double that, you know, somewhere in the about 80 degrees or so. And so we have two different years here. We were 2002 and 2003, and we had two different setup conditions in the spring. One year, for the lake to get the thermal layers, the water has to be still for a brief period of time while the temperature gets warm on the top. And if it remains windy, then sometimes it doesn't stratify. And Edmondson pointed this out back in the 50s when he was studying the lake, the limnologist from University of Washington. And we actually saw it. We were lucky because this year, in 2003, you can see there's pretty consistent temperature, so the lake mixes in the top layer down to about 14, 15 meters. And then you can see there's a boundary layer here where the temperature decreases rapidly. And then you see a little layer down here at the bottom, the cooler water at the bottom, and then it goes down into the chemical layer down in here. That was in 2003. In 2002, it was windy, it was warm, but it remained windy. There was never enough calm days for it to develop stratification, so you don't see this right here. You don't see this little layer right here, so it did not thermally stratify. So some years it does, some years it doesn't. I know in the paper that was published by the person that worked with Anthony and me, that he speculated in terms of climate change what impacts that might have, because you can see there's potentially more impact to this bottom layer when there's no stratification. It's not as protected because the whole lake is circulating above it, versus this year, it's just this part is circulating. So 1951-52 is when the lake began to change. That's when the Columbia Basin Irrigation Project began. They created Banks Lake and Long Lake and the West Canal, Bacon Siphon, and all those things. And so Banks Lake was built as irrigation storage, the Bacon Siphon, the main canal down here to Long Lake, and then I think the next maybe the next slide, I'm not sure. Yes, the next slide here we have the West Canal coming around to Soap Lake. And at one time they had planned to run it right across Soap Lake, and they did some drilling out in the middle of the lake, and they ended up running the siphon around off the coulee wall down around the north end of the lake, then back up the other side of the coulee back into the canal. And all this fresh water, so we have Lake Roosevelt up here, huge amount of fresh water backed up. And you think about all the percolation into the ground, and then we created Banks Lake, and all this water is being distributed into the fields for irrigation. So lots of huge new source of fresh water on the Columbia Plateau. And you can actually here you can see the West Canal dropping down the coulee wall, going around the north end of Soap Lake, and back up into the canal on this side. There's the siphon pipe there. That photo was from, I think it's from 1956. We got that from the Bureau of Reclamation office down in Ephrata. So there's the West Canal, just a picture of it. It's a pretty canal. But you can imagine, like water leaks out of the canal, water's being sprayed on the fields. There's lots of fresh water being distributed on the plateau. And so this is just kind of a time series that essentially demonstrates that. So going back, here's 1940, here's 2003 when we were doing our work, and just showing the blue line is lake stage, and measured, we put it into meters, but it could be in feet, but essentially it shows how lake level is rising, flooding the city of Soap Lake. And after Banks Lake was inundated, the West Canal was flooded and all this fresh water, and so you can see like it was encroaching here on the shoreline, coming to the shorelines are encroaching on the town. And they began, the Bureau of Reclamation began directly pumping out of the lake. Just put the pumps right in the lake. And so they're pumping the water out, but they're also at the same time pumping the minerals out that are present in the lake. So then there was more direct pumping right here. I think this was the early 90s. And there's lots of, back then they speculated, well, perhaps the lake is rising because we have a wetter period. And so that's part of what our grad student Jan Callis did, was he looked at, what is the relationship? And sure, precipitation did rise, but it went down. It was not really more than the average amount of precipitation if you looked at 5-year periods. And the precipitation certainly didn't account for that rise. It was inundation from groundwater. It was the amount of fresh water that was being added to the environment. So as a result of that, if we just look at the top layer, we just look at the layer that mixes annually, not the chemically dense bottom layer, it began to become more dilute. And so one way of measuring that is to essentially take a sample of water, dry it out, weigh it, and then dry all the water off of it. You can measure the amount of solids that are left. Those are called total dissolved solids. So they're all dissolved, and then you take the water off and you can measure the amount of solids that are left. So it's kind of one way of measuring salinity. And pre-1950, before this inundation of fresh water, it was on the order of 32 to 39 grams per liter. And if you think what that means is seawater, Puget Sound runs about 29, the Pacific's about 35, so it's essentially in the range of seawater at that point. And that's when the lake the wind would blow and you get some foam building up. By 1953, that dropped to 30. By 56, it was down to 20. And then it was stable from about 1958 to the period of our study at about half of what it was, at 17 to 18 grams per liter. So essentially the water had been diluted by about half. The bottom layer was not necessarily affected by this at that point. And I point this out now because this is really what the unique aspect of Soap Lake is. This is why Holly Pinker had the grant to study life in Soap Lake, because it has these extreme conditions. There's some new books that have just come out. They call organisms that live under these extreme conditions extremophiles. And certainly she has identified some extremophiles in Soap Lake. And what is extreme about Soap Lake, in the bottom layer, this layer beneath the circulating layer of the lake, is that it's salty, so 3 to 5 times the salinity of seawater. So it's when we look at total dissolved solids, it's on the order of 100 to 140. It's cold year-round. It's typically on the order of 4 to 7 degrees Celsius, which is like 40 to 46 degrees, something like 48 degrees Celsius, so it stays pretty cold year-round. It has no oxygen, not a bit of oxygen down there, and it probably hasn't had oxygen going way back to when it was formed, so life, existing with no oxygen. The sulfite is incredible. The amount of sulfur smell, the rotten egg smell, that was something that we would have to draw straws who was going to pull that sample up because it smelled so awful. It's toxic. Sulfite gas is toxic. Fortunately, we're very sensitive to it, so we tend to avoid it. But out there, you can't avoid it when you're pulling up samples from that bottom layer. So it has more sulfite gas than you can even imagine, which is toxic to most forms of life. It has a really high pH. So pH scale is 1 to 14, 7 is neutral, 4 would be about as acidic as natural waters typically get. This is at the other end. This is on the very basic end. So opposite of acid, it's very basic, and the pH is nearly 10. And people ask me, what does that mean? I come from the Midwest where we live on well water with lots of carbonates in it, and you take a shower and use soap, and you still feel soapy after you rinse off. And this is much more so. It's even hard to hold on to the equipment out there when it's been in that bottom layer. It just everything feels slippery, including your skin. So it's very basic. The alkalinity, the acid neutralizing capacity. So we measure the acid neutralizing capacity. You add acid to water, and the chemicals in the water will neutralize acid to a certain point. And typically, you might be on a scale of 50 or 100, something like that. And you use very dilute acid. We had used straight up concentrated acid. We had alkalinity running around 48,000 milligrams per liter. Might be a world record, I don't know. And fertility, like you think about all the things that live above this in the upper layer, the zooplankton and phytoplankton, as they die, they settle to the bottom. And if they settle to the bottom where that chemical, where that chemocline is, where that dense the old lake is, then they decay down there, and there's tons of nitrogen and phosphorus down there. So lots of nutrients, things that you put on your garden. So that's the unique aspect to it, is that bottom layer. That's the most unique aspect. Changes to the chemocline. So that boundary layer, one way to measure what's going on is the chemistry wasn't changing as a result of this influx of fresh water. That was affecting mostly the surface layer. But the bottom layer was being affected with shrinking. And they probably naturally shrink, but if you think in terms of thousands of years, and this was shrinking over the course of decades. And so you measure, it's pretty easy to detect where that boundary layer is. You can just lower down a probe that puts an electric current in the water, and when you have salty water, it really transmits electricity well, so suddenly your meter will take off, because I've hit the really chemically dense water. And so it's been measured over the years, back through the 50s, through 1972. They found that it had dropped a meter, 40 inches, a little bit over 3 feet, and that's pretty significant. That boundary layers, that means that the bottom lake is disappearing. It may not be diluting, but it's getting smaller. Some of it's going somewhere. 72 to 2003, total decline of 2.5 meters, so it's declined about 7 centimeters a year. 7 centimeters is on the order of about 1/3 of an inch per year, and rate of decline increased. 72 through 2003 is about 8 centimeters a year, and then we did the measurements in 2003. The total decline was 3.5 meters, which is about 10 feet, so it was now 10 feet lower than where it started back in 1958, and the decline was again about 8 centimeters per year. So the lake is being, that layer is dropping at about that rate, somewhere 7 to 8 centimeters a year. While we were out on Soap Lake, we had the old Bureau of Reclamation map from, I think it was 1955. And you can imagine back in 1955, they were using, they were shooting surveyors' transits and things like that, and going out with I think they used a brass chain to measure depth, and they constructed a bathymetric map. But we're astounded because there was no island on the map. And so that made us scratch our heads a little bit, like, I wonder how good that map is. That was the grad student, he photoshopped in that thing from the beach there. But still there was an island there, and we're like, there's an island here and it's not on the map, so maybe we should start with the basic hydrological tool being a map. And so, I should say, no, that's fine. So we think the island is probably, it looks to be like one of these, when we do the measurements around, it looks like one of these basalt columns that you see on the shore. And it's just in the water. So with GPS units and with electronic depth finders and all that kind of stuff, it makes the job a little easier because you don't have to go drive in straight lines and you don't have to worry about who's on the shore. You can just drive around, and that's essentially what we did. We recorded depths at about 700 points on the lake, made sure we got the island in there, and recreated the map. He did it through using geographic information systems. He developed a model. He struggled with that, got it done. And then we took the original map and compared it to our map just to see, like, how much different are they? It's always the question. So that just shows, like, that was the work we did. Created the map, so there's a nice bathroom map. And here's the...
Doing this all by itself.
Oh, that's okay.
There's a ghost.
So here's the deepest point in the lake. These are elevations above sea level. It's not 303 feet deep, it's 303 meters above sea level because the lake level fluctuates, so you don't really want to measure from the surface because it moves up and down. But there you can see, like, the deepest point, that's where that old lake exists, is right out there. So here's the city, or town of Soap Lake is down here, and here's our island right here, and there's where the old lake is. So
That little, and there's that little white spot where it says at the very top.
yeah, right here.
Oh.
Yeah. I think that's the island. We did some basic limnological measurements. I had maximum depth, 27 meters, which is on the order of 90 feet, 80 some feet. 1076 used as the elevate. I put that on there as the lake elevation because I think that's what the Bureau of Reclamation uses, is they try to keep the lake around the surface of the lake at 1076 feet above mean sea level. Historically, you look at the salt on the sides, it looks like it was as high as 1083, which is, what, 7 feet higher than that. So when it was flooding up during the 50s, it was flooding up. And I think they've sent, like, student workers down to search for objects under the water. I don't know how they did it, but they found some old sagebrush stuff, and they know it was at least as low as 1060 sometime historically. Anyway, so the real tool that you get out of the map is an understanding of what the volume of the water is in the lake at the various depths. So if you took the top meter of water off the lake, how much water is that? And you create a graph, and so this is the elevation above, this is above mean sea level. So, like, here's the bottom of the lake right here, about 303. And then you look at the volume of water in millions of cubic meters. And we compared what the Bureau of Reclamation had. This is the purple line is the 1955 line, and you look at the line we developed in 2002, and they're almost identical, which means the Bureau of Reclamation, using, like, stone tablets and chisels, like, came up with exactly the same thing. It was a great job by some engineers out on the lake doing meticulous work. So what that allowed us to do is that allows us to do some calculations. The Bureau of Reclamation has kept great records on salinity of the water that's being pumped out of the lake, volumes of water that have been removed from the lake. There's interception wells now along the shores, how much water is being pumped at any given time. And we know what the salinity is, and we can convert that to, in terms of pounds or tons of salt. In this case, kilograms of salt, and we can see that's, ignoring the black line, but just looking at all the dots going back to 1950 here, up through 2002, and you can see there's a general trend that there's still salts being removed. So this is the millions of kilograms of salt, and Jan figured about 5.6 million kilograms of salt per decade are being removed still. So the lake is still losing salt through those interception wells, and historically, of course, through direct pumping. But the lake salinity is still stable at about 17 to 18 grams per liter, and that's probably because it's probably a balance with whatever groundwater's come in and has some salt in it. So it's probably at some equilibrium with respect to that, but there's still salt being pumped out of the lake.
Could you repeat what you just said, please?
Okay. How far back? The
About
corollary.
No, about the maintained as far as the salinity.
So the salinity's been fairly constant for the past 3 decades, I guess. So the concentration, as we measure, I had a graph earlier that showed how it dropped and then it kind of stabilized. I think we'll see the graph again. But that doesn't mean that salt is not leaving the lake. It means there's salt leaving the lake, but there's a source of salt somewhere as well.
It's coming in and...
In the groundwater, perhaps,
Thank you.
or yeah.
Thank you.
Perhaps from the north. on through the upper lakes that still have some salt in them. We don't know where it's coming from, but we know this. We know salinity is stable, but we know that there's salty water being removed. We know from measuring the conductivity, measuring the salinity of the water that's being pumped. These were some of this. We found this way back in 2000, and I don't know when I probably first heard about Soap Lake. I looked into a web search, and you came up with Soap Lake, and it came up with this list of chemicals. And I see now with the Soap Lake Wikipedia site. Has anybody looked at that? It's got the same list of chemicals. It has some concentrations associated with it, but it's a broken link, so I have no idea what the source of this information is. But it was kind of unusual, and again, they're in part promoting the spa industry here. But just to point, some things like, well, rubidium would be it's radioactive. Probably not a lot of it, and it says oil on there, and copper and iron, and lots of kinds of salts. This made us curious. We see this kind of information, and we don't. Originally, it didn't have any concentrations. We're wondering, like, we should do some analysis on this. It turns out that bottom water, it cannot be conventionally analyzed. It's a little bit like Aunt Jemima syrup, I think, in terms of both the color and its pores thicker. I mean, it's really saline. It's 3 to 5 times the salinity of seawater, so it's got a viscosity to it, and it's got a definite color to it. And so you can't use conventional chemistry to do this. They kicked us out of we have a lab at Western that's a Department of Ecology certified lab for doing nutrient analysis, and after we did one run and dumped all the instruments up, they kicked us out. So we're going to come back to this. This is what the historical, some unattributed web source has this, that we're on the Soap Lake Wikipedia site. You can find it now.
So you're going to do more research on that?
We'll get to that. It's at the end.
Okay.
It comes up at the end, I think.
Doesn't want to leave that slide.
Yeah. Well, I'm going to talk a little bit about this. So here's Soap Lake. The town's down here. This is that old lake. This is the layer underneath. If you were to look straight down through the water and be able to perceive where it was in 1958, it occupied this portion of the lake. There's some bluffs along over here. We use those as kind of one of our landmarks to find that thing every time we went out and sample. Here you can see the West Canal. So it had an area of 22 hectares. And a volume of about 698,000 cubic meters. In 1972, measurements were conducted back then. Who was that, Anderson and Edmondson?
And Walker, no, 74 was Walker, so it might have been Anderson.
Anderson and Edmondson, I think. And so it shrunk a little bit. The area was 22, now it's 19. But more importantly, the volume. It was 698, now it's down to 491,000. So just a little bit of change in area, but a lot of loss of volume. And then if you click in, 2003, this is our measurement. It is now half the area, 22. It's down to 10 hectares. You can see the light blue right there. And the volume is about a fourth of what it was back in 1958. So it's down to 114,000 cubic meters. So, the area you think, well, it's not so much, but actually in terms of volume, like almost, it's down to about a fourth of what it was. Yeah, so there's a lot of the really chemically dense water is gone away. This again shows. So here's the salinity again, grams per liter. We started in the mid-30s. We're now at 17 to 18, and you can see initially back in the 50s when there was direct pumping, a lot of salts were being taken out of the surface layer. There was a big decline, and now it's stable for a long period of time, despite all the other things that have happened. The direct pumping that happened about right here doesn't show up. So there's salt being removed, but there is apparently salt being added at the same time. So the next thing that Jan did was he had all this information, and there's pretty great records from the Bureau of Reclamation. You've got the airport of Ephrata that measures precipitation and temperature. There was a humidity study done up on Banks Lake, and so he wanted to develop essentially some representative water budgets where you look at the relationship between inflow and outflow. And most lakes that's fairly complex because you got to measure the tributaries coming in, you got to measure the amount going out through the outflow streams, and Soap Lake is, it has none. So that simplifies things. So he picked these periods. This is the Grand Coulee Dam went in during this period, but they hadn't built Banks Lake, so he had data going back to 1940. This is the period when the West Canal and everything came online, and then looking at later, after more recent times. And you want to relate these things to the effects of all this water, all this fresh water that's being put into on the Columbia Plateau. We don't have to go into this in depth. It's actually fairly simple, because you think about, you want to know what the change in the volume of the lake was, and we have lake levels because they measure that, so you know what the lake level is day to day. And precipitation is going to increase that, so you have to add precipitation. Evaporation is going to decrease it, so you subtract evaporation. You add any inflows from tributaries, which 0. He said there's a few cases during some big storms where there might be some runoff from the highway, but essentially negligible. The outflows, so the streams going out, none. So that gets zeroed out. So you need precipitation, you need evaporation, and then you solve for groundwater. So you have groundwater in versus groundwater out. So typically in the hydrological model, or in the water budget model, you solve for groundwater, because that's the thing you can't really see, and it's the hardest thing to measure. So you measure everything else, and then by simple math, you figure out what the the change in groundwater is coming in versus going out. And that's essentially what that says right there. So precipitation from the National Weather Station at Ephrata, evaporation using a particular equation that deals with humidity and temperature. When it's less humid and it's warmer, you have more evaporation. So you use this Hammond equation, which was tested up on Banks Lake, so he had some local data to calibrate his equation. Withdrawal and input data, there's lots of that from the VOR, how much water is being pumped out of the lake. Salinity, we have that using, because they measure the salinity. And lake storage, we know that because we made that nice bathymetric map, and we made that graph, and we know versus where the lake elevation is, how much water, the change in lake elevation tells us what the change in the amount of water is. And so, this is very, kind of pretty, but a couple things to point out here. So, the blue is precipitation, and you probably well know you have very low precipitation here. You have a little more in the winter than you do in the summer. There were no withdrawals, so there's no, whatever color you call that, light yellow. You have change in storage, and so the lake would fill in the winter, it'd go up a little bit, and you can see this nice, it does this nice pattern like this. This is a 5-year average. And so the change in storage, the lake would be high in the winter as precipitation was more abundant, and then it'd be low in the summer as evaporation, kind of purple lines, became more prominent. So that would be a typical pattern, right, for most lakes. You have rain in the winter and it's hot and dry in the summer. This would be during the period, now we've got Banks Lake online, you've got the whole Columbia Plateau is being flooded, and so the big change here is the change in storage. So let's look at that. It no longer has that nice pattern where it's going, we go like this, and now we see the change in storage. Like we have negative in the winter, and we have nothing going, basically nothing in the summer, and then positive in early winter, back to negative in late winter. So it changed that part of the lake. It changed how it goes up and down during the course of a year. And the biggest thing would be the amount of groundwater. Just flip back to that previous slide for a second. Like you look at the height of the green bars here, and then forward, and now you look at the height of the green bars. So groundwater influx. If you subtract everything, you add and subtract everything else, it points to groundwater. And then we go to, the next series was in the 90s, and still pretty much groundwater influx has been somewhat reduced because of the interception wells that were installed after the direct pumping. And now we kind of have stable lake levels and stable salinity. And again, we've seen that graph, that's just a repeat of that graph where we have the direct pumping. This is, again, just going back to that same fact, this is another way to measure salinity using electricity. And it looks flat, but it's not quite flat. There's still a little bit, it's still decreased, the salinity is still decreasing just a little bit. Not as much as it did back when they removed water right from the lake. But there's still just a tiny little loss of salinity that's occurring in the surface water. That 5.6 million kilograms of salt per decade. So we asked the question about this the groundwater influx. How's it getting there? Where's it coming from? And we don't have a lot of data. We have some speculation. So this is what the lake would look like from the side. So here's Soap Lake from the side. Here's the surface waters right here. This is the old lake down here. This is from Bureau of Reclamation. Clay and mud underline the lake, which is fairly impermeable to water. So the lake is essentially pooled on top of this clay and mud liner. And below that, there's sand, gravel, and fresh water. We'll get to why we know that. And below that is the basalt bedrock. So we have bedrock below, sand and gravel deposit on top of that, and it's permeated with fresh water. We have a clay and mud liner, and then we have Soap Lake on top of that with the chemically dense part of the lake there and the freshwater part of the lake there. Bureau of Reclamation, when they were going to drop the siphon through the middle of Soap Lake, went out and drilled some holes. And this would be, the town of Soap Lake would be down here to orient you. So it was kind of down towards the south end of the lake. They punched holes down through the clay to find out about the suitability to put a pipe through there. And you read we have the account, and they talk about the water emerging from the pipes, tasting as fresh as any artesian well water, which is where we get the idea this is fresh water down here. They basically punched through, artesian effect, the pressure from the aquifer drove the water up, and for whatever reason somebody drank the water. And they said it tastes as fresh as anything you can imagine. So it was not Soap Lake water, it was something below that. So this is partly where that model comes from, that they drilled down through this clay and mud. When they decided that it was not going to be suitable to drop the siphon through the lake, they say they attempted to backfill those holes. We went out and looked for the holes when we were doing our lake surveys, when we were doing our bathymetric mapping stuff. We could not find evidence of where they are. I don't know how big they are, or what if you can imagine trying to backfill something against pressure like that. We didn't think it would be that feasible, but we couldn't find. But that's one potential source of some of the fresh water coming into the lake. Potential source. No, I'm not saying it is. I'm just saying that we're speculating because we know that they drilled holes, and we have this narrative that describes the water coming forth and being fresh. The other thing, we were out there in January sampling. It's funny, I think we're like the only people on the lake in January. And but there was a guy out there in a kayak. We almost never saw anybody out there, and I think he was a retired oceanographer from South Carolina. Does anybody know who that is? And he said, surely you've seen the Soap Lake volcano. And we're like, oh, we will now. Soap Lake volcano. And he said, go up to the north end of the lake. There's a milk jug tied off up there. You just find the volcano. And so we did. This would be about where it is up here. So we motored on up there after we collected our sample from, we're collecting our sample from the old lake, which is about right in here. And I think the next one might be a picture. So there's the boreholes in the south end of the lake here. And so there's this thing, this feature nearly at the surface of the water, and there's the milk jug tied off on it. And there's water that you can even see, like this little thing right here. This water is gushing up out of this hole in this thing, this big piece of chunk of whatever. And so we broke off a little piece of it and took it back to the geologists. And they poured some acid on it, and they said, well, this appears to be calcium carbonate. So it looks like it's a giant calcium carbonate column. It's in about 14 feet of water. And we stuck our instrument in there to see, like, is this Soap Lake water coming up, or what is this? And it was not Soap Lake water. It had different salinity. It was fresher water. It had lower oxygen. It had not the characteristics of what we'd expect for Soap Lake water. So there's the Soap Lake, I don't know, do you call it the volcano? Who knows of it? Is it the volcano?
The underwater volcano is what we call it.
Yeah, it's an underwater volcano gushing fresh water into the lake. It's a calcium carbonate column. It probably had dissolved calcium carbonate somewhere below the earth, and as it cools it in, whatever goes on, it's precipitating is this, limestone is what calcium carbonate is. So it's a little limestone column there with a hole in it that has water coming out of it. We didn't we went and visited a couple times. We tried to measure the volume coming out of it, but we couldn't tell. There could be other holes and things. And, we came up with an estimate, but I would say it needs further investigation. This is just a view of the Soap Lake down here, and of course all the crop circles and things, just the amount of fresh water that's going into onto the basin here. So this is the last thing. This is the chemistry. So as I said, it clogs up most of the instruments. It's difficult to analyze. We had to go back to some really old methods to do the nutrient analysis, and we had to do that in our own lab since we got kicked out of the certified lab. We sent this out to AmTest. It's a firm in Seattle at the time. They used what's called, they have an inductively coupled plasma mass spectrophotometer, the ICP-MS, inductively coupled plasma mass spectrophotometer. And they weren't so common back in those days. We have one at Western now that I occasionally use, but it won't tell you what kinds of things you have in terms of compounds, but it will tell you the elements that are present and the concentration of those elements. You don't know, for example, if you found nitrogen, you don't know if it's nitrate or nitrite or ammonia, you just know you have nitrogen. You don't know what compound it might be present as. And so you get elements, you get a list of elements. And so we sent a sample up because we'd seen that list on the web of what the Soap Lake compounds were. And so I selected the ones here. These are the top ones that were all more than 1 milligram per liter. There's a lot more of them in the list because they can measure down to parts per trillion. So they can measure pretty small amounts. This would be parts per million. 1 milligram per liter would be 1 part per million. And so I selected the chemicals that came back. We sent out 3 samples. We sent our initial sample, we just used the bottom water, and we want some assurance that what we were seeing was really what was there. And so we sent off a sample from April and another one from May of 2005, or from April and June of 2005. And lots of sulfur. We knew there was lots of sulfur. Like, it smells like sulfur. This is from the top layer. So these are the 2 samples from the top layer. This is April, this is June. And these are the bottom layer. And so sulfur, you can see sulfur, 1,200 parts per million, 1,000 parts per million. You go to the bottom water, like, I'm not sure what happened there, but there's 87,000 parts per million, which is exactly what it smells like. Sodium, 69, so this is about, what, 7 or 8 times as more sodium in the bottom, in that old lake, as there is in the surface water. Potassium, same thing, you have in the hundreds here, you have in the thousands here. Phosphorus, lots, as I say, lots of phosphorus down in the bottom water. That's from a person who studies chlorophyll and phytoplankton, like that's a ton of phosphorus. That would be, you take a cup of water and put it on your garden, that'd be awesome for it. Silica was kind of the same. Silica is used by some of the phytoplankton here, and it's pretty much the same. It's dissolved glass, essentially. And you can see that's pretty much the same at the top and the bottom. Same for magnesium, same for calcium. Pretty much the same on the top and the bottom. And the one thing that stood out, this is the only one of the kind of the micro elements that stood out, was arsenic. Because in the bottom water, there's about 2,400 micrograms per liter, or 2.4 milligrams per liter of arsenic in the bottom. There's about 1/10 of that in the surface water. And the EPA has criteria for aquatic life. And they don't have any criteria for any of these because these usually aren't considered all that of much concern. But arsenic, we've heard of it, arsenic and old lace. And so they have aquatic criteria, 0.15. So if you compare these numbers to 0.15, so that's about 3 times that, that's twice that, that's 15 times that or so. So there's a fair amount of arsenic, which from a scientific perspective, that is extraordinary. When you think about the things there are things that live in Soap Lake, there's some zooplankton, some phytoplankton, they're living there with that amount of arsenic. They've adapted to that amount of arsenic. The EPA criteria is meant to, it would be the amount that would preserve all aquatic life, like fish and phytoplankton and all the kinds of things that might live in the water. And these are levels that are way in excess of anything that most aquatic life experiences. And so that's the unique aspect of a meromictic lake, is you have these extreme environments. And it's not just the extreme in terms of kind of gross chemistry, like pH and alkalinity, but it's in terms of these micro things that you find that would be considered toxic in any other environment. But here you have life that's evolved to adapt to those concentrations.
Leo, is that historic, or is that from the orchards? The arsenic?
Oh, the arsenic? So there's arsenic. I mean, arsenic is a naturally occurring, we don't know what mineral it is. I mean, it's likely arsenate, but it naturally occurs in geology. I mean, it's a geological source. No, this would not be from the orchards. No. No, there's a geological source. I mean, there's different places. There's lots of places where arsenic has been studied, natural arsenic occurrences in India and China. and some other places, and you happen to have some that's probably somewhere here in the plateau that has been percolated down through the eons. So, Jan's thesis work, Dr. Callis now, he's not on, got to get a PhD. The interception wells have restored the level of the lake to equilibrium, where you're not flooding the town anymore, and it's not going way down, it's not going way up. They manage those wells. But, in terms of the salinity, there's still salts being removed from the lake through those interception wells. The theory is if you put the wells back in the shoreline, that you'd intercept this water coming down the slopes before it gets into the lake. But if you can imagine how a well works, you sink the well point and it creates a cone of depression around it as it sucks water, and it's going to probably get some Soap Lake water. I mean, you can't just intercept one side of it. There's like, it's the whole groundwater table. And so, there's some salt, there's still salt being lost. It appears that the salinity is not changing, although the constituents might be, because there's probably some salt coming in. There's salts, there's fertilizers, there's all kinds of sources of salt up on the plateau. The bottom layer is shrinking. Chemically it's stable, but size-wise, it's down to about 25% of its size, what it was back in the 1950s. And the correct answer is E, all of the above. So, and I think that's the last slide.
That's the last slide.
Okay, thank you.
It's not the last part of it.
Oh, the acknowledgements, of course. So, Dr. Robin Matthews, she runs the lab that we screwed the instruments up in by using Soap Lake water, so we thank her. Sally Abella was one of Edmondson's lab techs way back in the day, and then she worked for King County Surface Water Management, and I think she recently retired, right, Tony?
Yeah.
And Arnie Litt was also in Edmondson's lab, and so we got to go to Edmondson's, what would you call it? His catacomb?
Yeah.
Yeah, we were in the basement of the building that was in. They put it all this, it was sort of like a shrine. Like they gave us access to all the file cabinets and everything else, everything that he'd saved all his correspondence and other people's dating back, people writing letters from Soap Lake to him.
And water samples.
Water, the water samples are
Well,
done.
McKay had water samples for years, and then,
Yeah, they're in the nursing home down here.
yeah.
We grabbed the Soap Lake ones. There's still Blue Lake and some of the other lakes in there. The Bureau of Reclamation, they were very cooperative on the FREDA office. And,
John Moody's in the audience.
John?
Sorry, John.
Yeah, you got shout out to John. And Soap Lake Conservancy, of course, throughout. And funding provided by the National Science Foundation grant that Dr. Pinker, Dr. Mormia, and Dr. Payton received. I think, are you here?
Is Melanie?
Is Melanie here?
No.
She's been corresponding with me the past week, so I wasn't sure. And then lots of people have worked on Soap Lake before us, and so these are the list of people, all the information that we were able to get about Soap Lake from these authors. Yeah.
I have a picture.
Well, there it is.
I'm sure there would be questions,
Here's a
but
question right here.
I also have, because this was a lot of heady stuff, and I wanted you to have time to think about questions and get them clear. We have a special treat of a song.
A Soap Lake song?
Yes, that was written by Don Johnstead, and he's here. And would you like to do that now? Because I think it will give people time to really get your questions clear. And it's a very brief song, but it's about Soap Lake that he wrote for the sundial and the lake.
Okay, so
A little right brain time for you to sink in to all the left brain stuff that we just had for the last hour and get clear about the questions you have. This actually was written for the dedication of the sundial, as I recall. Other people know better than I about that. And also, I'm going to get you some water.
so what is the status of the lava lamp?
There's people better knowing about that.
Tony and I want to get the coffee franchise that would go in the ground store. That would be called Lava Java.
Yeah. How many of you have seen the mural on the alternative school with the mastodons running? That's kind of my inspiration for this song. I can't imagine what it's going to be like.
You can also take a moment to stand up and stretch. That helps get all that stuff from our body. It takes